In this lesson, we're going to look at how temperature affects reaction rate in the context of collision theory. So we remember from the last lesson that for a reaction to occur, the reacting particles must first of all collide with each other. If they don't collide with each other, then there will be no reaction. So that's the first really important requirement for a reaction to occur. The second thing which must happen is that the kinetic energy of those particles must supply the activation energy required to break the bonds present in the reactants so that the particles can react with each other. So for example, here we have two molecules which are on a collision course. They're on line to collide with each other, so a reaction is imminent, but what we're saying is that the kinetic energy of these particles, let's call that one kinetic energy 1 and this one kinetic energy 2. Okay, the kinetic energy of these two particles must be greater than the activation energy required to break the bonds. And so if the kinetic energy is greater than the activation energy, when they collide, the bonds will break, okay, and the individual particles will then be able to combine with each other to form the products of the reactant. Okay, so first of all, the particles have got to collide. Secondly, they've got to have enough kinetic energy to break the bonds. That's to say, the kinetic energy of the individual particles has got to overcome the activation energy required for that reaction to take place. And if that happens, then a reaction will occur. But our question is, what affects the rate at which reactions occur? How does temperature affect the rate of reaction? So let's just consider the following diagrams. Okay, so here we've got the particles of two different reactants and they're both at different temperature. So in the first case, the reactants are at a lower temperature and here they're at a higher temperature. So what does that mean? Well, you'll notice first of all that in this case the particles are going to be moving slower because they are at a lower temperature. And you remember that the average kinetic energy of particles is directly proportional to the temperature. So if we've got a lower temperature, then the average kinetic energy of these particles would be lower, so they're moving slower. That means that they collide with each other less frequently, so there are going to be fewer collisions. And when they do collide, the collisions on impact will have lower kinetic energy. What happens if we increase the temperature? Well, we give the particles more kinetic energy. That means that they're moving faster. Right? That means that there are going to be more collisions because they're moving faster. So there's more chance of a reaction occurring, and when they do collide, their energy on the impact will be greater. So there's more chance of a successful collision. That's to say that the collision will result in the bonds being broken and the activation energy being overcome. So move faster, more collisions, more kinetic energy on impact. So what we can say is then, as the temperature increases, following this collision theory, the reaction rate or rate of reaction will also increase. So a simple experiment which might demonstrate this fact, this dependence of reaction rate on temperature, is the following. Okay, we've got two identical aqueous solutions of hydrochloric acid, dilute hydrochloric acid, and in each solution we've got an identical piece of zinc, for example. And you'll know that when zinc is added to hydrochloric acid, it will react to produce zinc chloride, a solution of zinc chloride, and hydrogen gas will be liberated. So what we're making sure of in this demonstration is that the concentration of hydrochloric acid is the same, that the amount of zinc, that's to say the surface area of the reactants, is the same, that in this particular case we're not using a catalyst of any form, but what we're going to change is the temperature of the reactants. So we'll say that in this case the dilute HCl is at a temperature of 20 degrees Celsius, say room temperature, and in this case we've heated it up to 80 degrees Celsius. Okay, so if we do this, we'll immediately notice a difference in the reaction rate. So you're going to notice bubbles of hydrogen being liberated as a result of this reaction, but in the case of the acid that's at 80 degrees Celsius, the hydrogen gas is going to be liberated at a much greater rate. Okay, so the bubbles are going to appear much faster in this case. So in the second case, hydrogen is liberated at a faster rate because the reaction takes place at a faster rate because the temperature is greater.